All right, well, welcome everyone. I am JJ. Let's tackle an example problem. So we're coming in and saying let's use our area method rather than our equation method to make our shear moment diagrams for our beam that we have here. Again, we just go left to right across this and apply all of our rules. If a force goes up, our shear immediately goes up. If it goes down, our shear immediately goes down. Forces aren't going to cause an immediate change in our moment diagram. For couple moments, they'll do nothing to our shear diagram, but a counterclockwise couple moment makes our moment diagram immediately go down. Clockwise makes it immediately go up. For distributed loads, we can say our shear at the end of a distributed load would be the shear at the beginning plus the area. Our moment at the end of a shear area is our moment at the start plus our area of the shear. So we can come in and work through everything in there. So let's just start going left to right across this. We're given our support reactions in here. If these would be a challenge for you to find, I would tell you, go back and watch earlier videos. But for this, just to move everything along, we're just going to give them to us. But so as we start, we're going to start on the left edge and work to the right and just resolve every time something shows up what we need to do. So if we're starting in here, we always are going to start at 0. But before we do this, let's actually find our area. We have one distributed load in here. Let's call that area 1. And we'll come off to the side and find area 1. Area 1 is a rectangle. It should be the area 1 equals, well, the area of a rectangle is base times height. Our base is 4. The height is 100. 4 times 100 is going to get us 400 equals 400 pounds. From there, I can start going left to right across my diagrams. So I'll start at 0. Let's put a dot in there right at 0, at the origin for us. We're starting at 0. And then we can come in and say, well, as I start to move to the left, there's a 200-pound force. It points down, so I'm immediately going to decrease down by 200. So we'll drop down to negative 200. 200, negative 200. But I stay constant in this because there's no distributed load until we get to A. So the integral of 0 is a constant. We go constant until we get to A. At that point, I have both AY and a distributed load starting. AY is applied in an infinitely small area. That area 1 is over a 4-foot distance. So we'll resolve that instantaneous thing first. So negative 200 plus AY will immediately go up by AY. Negative 200 plus 375 gets us here at 175. 175. From here, we have a distributed load. So our area, or our shear at the end of that distributed load at B should be our shear at the beginning. We take that last point that we plotted, so we don't use negative 200, we'll use 175. So 175 minus the area of our distributed load. 175 minus area 1, 175 minus 400 would get us negative 225. So we can come down and plot that point, negative 225. We have a constant distributed load. If I integrate a constant, I get a linear function. If I integrate 2, for example, I'll get y equals 2x. So I can make a linear function here. Let's start shading this in. But that gets me my first handful of intervals in there. I sloped across the x-axis in this. So this point right here, where my shear is 0, that's going to become a max or a min point in my moment diagram. So I'm going to mark that. I'll need to find distances to it. We'll get there in just a second. At that point, at B, I have my roller. By, I know is 225. Negative 225 plus 225 will get us to go up immediately, pushing us back to 0. And then there is a little bit of beam left. I would say from B to the right edge, there's no distributed load, which means I'm constant for my shear. I'm going to go constant until the right edge of this, where I have a couple moment. Couple moment doesn't do anything for our shear, so we just stay at 0 here. And that would finish up our shear diagram. To get our moment diagram, I'm going to come in and do one thing. I tend to forget couple moments in here, so I would come in and just to help me remember, I'm going to draw in a clockwise, because it goes clockwise, arrow here at the far right edge, because that's where it's at. Again, it just helps me remember, hey, there's something else here, you should look up above. But then I need to figure out a handful of areas. Area 1, 2, 3, and there's no area here. So 3 more areas. We have 1 actually. So let's call this area 2. Area 2, area 3, area 4. To get areas 3 and 4, we'll need the base. To get that base, we can just come in and say, let's find our distance to where that shear is 0. So we can come in and call that, I'll mark it here. What's this distance? And this one. 2 distances in here. Let's call this x1 and this one x2. Just 2 distances. They're kind of squished in there. Let's move that 175. It'll give us a little bit more room to figure out what we're working with here. This is x1, and we're just relabeling 175 over here. I can find x1 and x2. If I just keep shooting that point straight down, it's going to get to a max or a min point in my moment diagram. So that's going to become important for us. We should expect something important here. But I can find x1 and x2 using proportional triangles. In my first triangle here, my ratio of base to height is x1 over base 175 height equals, in our second triangle, our base is x2 and our height is 225. And we're just going to take that as a positive because it works out so we don't get a negative x. But this is equal to our ratio of the total change in x over the total change in y. That total x distance, x1 plus x2, well, that's 4 feet. 4. And that total change from 175 to negative 225, well, that's just area 1, 4 over 400. And I can solve that for x1 and x2. I'm going to get that x1 is 1.75 feet. And I'll get the x2 is going to be 2.25 feet. And I'll have to work with those to actually come in and find my areas. Let's go ahead and find all 3 of our areas, the last 3 I need. Area 2, our rectangle, should be base times height. The base of this is 1 foot. Our height is negative 200. So this is area 2, negative 200 is equal to negative 200 pound-feet. Area 3 is a triangle, so we should have 1/2. Our base is x1, 1.75, times our height is 175, 175. Or this will get us, the area 3 is 153.1 pound-feet. And then our very last area, area 4. Also a triangle, so we'll still use 1/2 base times height. Our base is x2, 2.25. And our height is negative 225 times negative 225. Will get us that this area is negative 253.1 pound-feet. That's everything that I need. I can now start working left to right across my moment diagram or across my pieces here to get the moment diagram. So again, just like always, we will start at 0 on this. So get our dot there at 0, at the origin. There's no couple moment, so nothing is going to make us jump away there. So we can go on and say, well, my next thing will be the moment at the end of area 2. Should be the moment at the beginning of area 2, the moment at the start, plus area 2. Or that would be 0 plus a negative 200, area 2. 0 minus 200 would get us to negative 200 down here. And I can label that point, negative 200. I had a constant for my shear. Integrating a constant should give me a linear function. So I just slope downwards to negative 200. My next point, I could come in and say, well, my moment at the end of area 3 should be the moment at the start of area 3, negative 200, plus area 3. So negative 200 plus 153.1 is going to get us negative 46.9. So I can come in and label another point in here. Negative 46.9. And that should be a parabolic function. Because we had a linear slope here, linear function. If we integrate linear, we're going to get a parabolic function, a quadratic function. So we're now at negative 46.9. And we can go to area 4. Our moment at the end of area 4 should be the moment at the beginning of it, negative 46.9, plus area 4. So negative 46.9 minus 253.1 is going to get us down here to negative 300. I'm going to label this off on the right edge. Negative 300. So we can curve, continue our parabola. We're going to drop back down to negative 300. In this last interval, there is no shear. If I integrate 0, I get a constant. My moment should go constant. Which gets us to, we have a couple moment that's being applied here. It's going clockwise. If we look at our rules, this one always confuses people. But a clockwise couple moment should make our moment diagram immediately go up. So we're going to go straight back up to 0. Closing out our moment diagram. We are starting and stopping this at 0. We always should be doing that for these. But hopefully this is a helpful video for you. If it was, stick around, hit those like and subscribe buttons. Let's get you in with JJ.